My name is Arvind, and besides being an executive associate dean in the college, I'm also a professor in mechanical engineering and by courtesy in materials. Now, as Purdue Engineering pursues its path to the pinnacle of excellence at scale, we will continue to refine our intellectual focus to be at the interface of the virtual and physical side of engineering, while significantly growing along the directions of the five Purdue Engineering initiatives. Now, ICON, the Center for Innovation and Control Optimization and Networks, as Shreyas pointed out, is a part of the Purdue Engineering Initiative on Autonomous and Connected Systems. It really has a broad mission to integrate classical theories in control optimization and networks together with advances in AI learning data for research and education in complex autonomous and connected systems, with the larger goal to be in the pursuit of innovative solutions, as Shreya said, to grand challenges, be they in manufacturing, transportation networks, healthcare, supply chains, power and communication systems, or social networks. Now, ICON is co-directed by our rising stars, Professor Shashwat Mo in AAE and Shreya Sundaram ECE, and has 52 faculty members in 8 schools and departments at Purdue. Now, without, I should quickly go to introducing our distinguished seminar speaker for today, Professor Tamer Basar. Tamer Basar has been with the University of Illinois Urbana-Champaign since 1981, where he's currently the Swanlund Endowed Chair Emeritus and Center for Advanced Study, Professor Emeritus of Electrical and Computer Engineering, and also has affiliations with the CSL, the Coordinated Science Laboratory, Information Trust Institute, and Mechanical Science and Engineering. Professor Basar is a world-renowned expert in dynamics, in systems, control, communications, optimization, networks, and dynamic games, and his current research interests are in stochastic teams, game networks, multi-agent systems and learning, data-driven distributed optimization, epidemics, modeling and control over networks, security and trust, energy systems, and cyber-physical systems. Over his distinguished career, he's received several awards and recognitions. He is a member of the U.S. National Academy of Engineering, fellow of IEEE, IFAC, and SIAM, past president of the IEEE Control Systems Society, founding president of the International Society of Dynamic Games, and past president of the AACC, and he has received the IEEE Control Systems Award, ISDG I6 Award, AACC Bellman Award, IFAC Quasar Medal, IEEE CSS Bodie Lecture Prize, and a number of recognitions from academic institutions, including the Wilbur Cross Medal from Yale. And he does hold several honorary doctorates and fellowships from international institutions, the most recent one being from KTH in Sweden. So it is really an honor, Professor Basar, to have you here joining us for the ICON series. And without further ado, please join me in welcoming Professor Basar.
Thank you. Thank you for this generous introduction. It's a pleasure to give this lecture, and congratulations to ICON and for the successful, I guess, the anniversary. I heard that it has been just 1 year, so this is a celebration of the first year's anniversary. Let me, before I start my talk, let me say a few words about Kishan, whom you have heard that he passed away a couple of days ago, and which was a shock to all of us. And he was in extremely good health and was a marathon runner, and he used he attended our conferences quite regularly, and every time I would see him in the morning, he would be coming back from jogging. So wherever he goes, whatever venue he's at, he always took it to just exercise. So it's very unfortunate. And it's a big loss for NSF, a big loss for our community, control community, dynamic systems, and generally the intelligence systems and all related fields. I know him from way back in the early 1980s when he was at General Electric, and he was working on applied problems, but I particularly became aware of his work on implementation of Kalman filtering, parallel implementation, and using reducing the computational effort there, which had important applications in industry, particularly at General Electric. He moved to NSF in the late 1980s, I believe it was 1989, and he became a program director in the electrical engineering and systems department, actually electrical and communication systems division. He was a program director there. He was in charge of control, and more recently, at the time of his passing away, he was handling proposals in the control and sensor networks, in the power controls and adaptive networks program within the ECS, Electrical and Communication Systems division. He had many initiatives which the community has benefited from. What I remember is intelligent control was one of them, and he was instrumental in CPS as well, initiatives. And he was someone who cared for particularly the younger researchers and tried to help them in many different ways. And control theory has evolved tremendously, actually, since the day he joined NSF. So that has been 30 plus years. And he was really wrote that evolution of control theory and broadening of topics, and he was very open-minded and really pushed the people he was funding in exciting directions, which would be also touching on several other fields, and more recently, of course, the learning and artificial intelligence and connecting with computer science and so on. So it's a big loss, and I was really shocked to hear a couple of days ago that he had passed away. Okay, so coming back to the ICON lecture, this is, I decided to talk about something that we have recently worked on, and we are continuing to work on, and that's policy optimization problems, which has connections to machine learning, and particularly reinforcement learning. And this is a specific problem which I'm going to discuss, but it has extensions in many different directions which we are exploring. And this is joint work and still continuing with a PhD student of mine, Kai-Ching Zhang, who is about to complete his studies, and my colleague at Illinois, Bin Hu. So the outline of my talk is as follows. I'll first provide a brief introduction to reinforcement learning, known as RL, the acronym in the broad community, and policy optimization, which is an essential tool for it. Particularly, I'll focus on policy optimization in controller design and bring in robustness considerations, which people have only recently started to worry about. And I'll be talking about what's called the mixed design problem, where you minimize the H2 norm for a dynamical system subject to some robustness bounds. And these robustness bounds are provided by the H infinity norm. And there's a strong connection to risk-sensitive controller design. Now, the mixed design is a deterministic problem, and with sort of worst caseness embedded in it. And whereas the risk-sensitive controller design is a risk-sensitive control problem, is a stochastic problem. But there is a very strong connection between the two. So what I'm going to talk about, if you are just interested in risk-sensitive controller design, that everything applies to it. And but if you're not interested in stochastic systems, but only on mixed designs, then again, the same tools apply to that, because there is an equivalence in the sense that I will discuss. There are several challenges actually when you try to do policy optimization for such problems, and one of them is that they are non-convex. So any optimization tools that are used that have been developed for convex problems, convex optimization tools do not apply here. And the other one is, which is sort of more serious, is the lack of coercivity in these when you bring in robustness bounds, and that essentially means that if you decrease the cost function, that doesn't necessarily imply that you are going to stay within the feasible set. And that is, for example, satisfy the H infinity bound. So we have something that we have introduced, implicit regularization, to overcome that. And so there are, of course, one has several candidate policy optimization tools or methods or algorithms that one can use. And we show that two of these, which will become clear later in the talk, actually have convergence properties and have this implicit regularization, which means that you stay within the feasible set, and they have sub or super linear rates depending on where in the feasible region you initialize the algorithm. And then I will, as time permits, talk a little bit about robust adversarial reinforcement learning, and which has connections to zero-sum games, and the zero-sum games have connections to risk-sensitive control design. So everything ties together. And then talk about some extensions and conclusions. So the reinforcement learning has achieved, as most of you know, tremendous success in sequential decision-making problems, and as well as in continuous control tasks, such as the game of Go, video games, and robotics, all very well known. And most of these successes, they hinge on the algorithmic framework of policy optimization. So it's you approximate functions, and this way you are able to handle large continuous spaces. And policy optimization is fairly easy to implement and is scalable to high-dimensional control systems. And it also enables the data-driven sample-based search. And we do have, within the framework of this talk or the model that I'm going to discuss, we have some recent work on sample-based search, that is derivative-free methods. But I won't have time to go into that. That's still ongoing research. Some prominent examples where policy optimization works is the reinforced, the actor-critic algorithms, natural policy gradient, and the deterministic policy gradient, the test region policy optimization, and proximal policy optimization. Now, my interest here, as I indicated, is optimal control, or doing policy optimization for control problems. So what's a standard optimal control problem? You have a performance index. Let's say that you have an infinite horizon problem. That's what I'll be dealing with. And you have a state equation, and you have a control ut, which at each time t belongs to some constraints. So you want to minimize this function. And so the policy optimization approach, essentially, what it does is you take the controller, you parameterize it in terms of a finite number of parameters, and theta, let's call this theta. So if you substitute this in, then you have your cost function as a function of these parameters, and then you apply sort of policy optimization to these parameters. Now, one special case is the linear quadratic regulator problem, when f is linear and the c is quadratic, and there's no constraint on u, so it's an m is the dimension of the control, so u is equal to rm. In that case, the parameterization is very natural, because we know that the optimal solution under some stabilizability conditions is a linear function of x, the feedback, the best feedback solution. So you have a natural parameterization where k, so you can substitute this into your cost function and then do policy optimization with respect to k. So you are not, if you can obtain the true value, the real optimal value of k, then there is no loss due to parameterization in that case. Okay, so that's the advantage. Whereas if you have a nonlinear problem, it very much depends as to how close you come to the minimum value of j, depends on how your parameterization is. But for the linear quadratic regulator, that's not an issue. Now, the downside of optimal control, and particularly the LQR, is that it's not robust. If you have modeling imprecisions, if you don't know the model exactly, if there are disturbances which you ignore or noise, then the solution is very sensitive to such changes, and the system could, in fact, even go unstable. So what one introduces to avoid these sort of difficulties or the undesirable behavior of the system is robust optimal control, where you optimize, again, an objective functional, but subject to some additional guarantees of robustness. And how can one model robustness? And one of them is to bring in risk-sensitive control. And this is what I'll make that clear, what this is, for those of you who are not familiar with it. The other one is, which was in the 1980s. This was an approach that people in control theory used, and the comprehensive theory was developed, is the H infinity norm constraint that you can impose, and so which means that you are bounding any unfavorable inputs that could enter into the system, and the other one is the worst case disturbance, the zero-sum games. In other words, what you do is the unknowns, you model them as being controlled by an adversary, and then this way, instead of solving a single agent optimization problem, single controller optimization problem, you are solving a game where the controller plays against an adversary. So I'm going to talk about three of these and the connections between these. Now, all of these could actually be unified within the framework of the H2 H infinity mixed design, which means you are minimizing an H2 norm. That's your objective, subject to an H infinity norm constraint. And the challenge of doing policy optimization for such problems is that it leads to a constrained non-convex optimization problem. So the reinforcement learning problems or many optimal control problems can therefore be written in this following form, where you have or formulated in this way, where you have an objective function, which depends on the parameterization. As I indicated in linear control problems, then the parameterization is a natural one. And so you minimize over that gain k, subject to some constraint. And the constraint set script k depends on the, of course, nature of the problem, and sometimes it's implicit, but it's very important. And for example, in the linear quadratic regulator problem, let's say in discrete time, this is the dynamic, this is the system equation, and then you have a quadratic cost function. And so what you require, so what the set looks like, is that you want the closed loop system to be stable. So in other words, you are looking for a solution within the, you are looking for the best k in the space of all matrices which satisfy this spectral radius condition, that essentially stability of the closed loop system. But this is a non-convex constraint. So immediately you have non-convexity coming into the picture. And when you substitute k in here, again, you have a highly complicated solution. But still, this is a fairly, relative to what I'll be talking about, is a fairly simpler problem. Now, there are other examples of constraints. You can have, for example, even in the context of LQR, but if you consider an extension of that, you have boundedness of K's norm. You can have you have truncations on the gain, and so you look. That's an additional constraint in addition to stability. Or you may have safety constraints on states. That is, you don't want the system state X to go at any point in time outside a certain Q. Okay, so that will bring in other more complicated constraints on K. Now, why are we interested in robustness? I hinted this. Most control systems are safety critical. And so therefore it's not only stability, but also the robustness that one would be interested, one would look for. And I mentioned H infinity optimal control theory from in the 1980s and 90s. And essentially this is your plant, and then this is your control gain, K, feedback control, acting on the output. And but you have some unmodeled part of the plant which is summarized in this upper block, and so delta is the perturbation around the plant, P, and you want to design controls such that provided that this satisfies some bounds, and I'll make that clear shortly, that you still have an optimal solution. So what you look at is the closed loop transfer function from the output to the from the disturbance to the output Z, and let me denote this by T of K, and again it depends on K. Now this is known as the G delta model. G is your nominal system, and delta is the perturbation around the nominal plant. It covers many robustness considerations in control. You can parametric uncertainty in A and B, for example, in terms of like delta A, delta B. You have some nominal values of A and B, and then you wrap around this uncertainty block with delta A and delta B. You can have time varying parameters AT and BT, or even time varying delay in terms of X, and even dynamic uncertainty. This could be delta, could be a dynamical system, which may be of unknown model order. So there are various sort of scenarios that this would capture. And H infinity norm is what one uses, and the basic theorem, which is due to James back in 1966, is that if the H infinity norm of Tk satisfies a bound gamma, and if these perturbations from L2 to L2 discrete time is less than 1 over gamma, then the overall system is input-output stable. So therefore, the product of these two should be less than 1. And so therefore, in addition to, if we want to bring in some robustness considerations into the problem, I have to change my constraint set on K, not only involve stability, but also involve some robustness. So therefore, in addition to the spectral radius of the feedback matrix being less than 1, I also have the H infinity norm from the disturbance to the output to be less than gamma, where gamma is a chosen parameter. And as I indicated, the smaller gamma is, the larger would be this, but up to a point, of course, would be the allowable perturbations around the system. So this is what we call the strong robust stability. And clearly, as you let gamma go to infinity, which means you essentially are removing this, what you have is essentially the constraint set is the stability region in the LQR problem. So now the main question here, the main challenge is how can we enforce during the policy optimization, how can we make sure that at every point of the iteration, we stay in that constraint set? That is how to enforce or maintain robust stability. During the learning process, for example, if you don't know the model of the system exactly or the model parameters. And the second question is, okay, if we stay within the constraint set, if we can ensure that, what are the, do we have global convergence? Note that it's a non-convex optimization problem, and the constraints are also non-convex. And what are the rates of convergence if we use policy optimization? And so that brings me to the real meat of this talk, which is this robust mixed design. And I have to cite this paper here, which was presented. It was presented at the conference L4DC, which was the first one in the series last year. And of course, it appeared in the proceedings, Machine Learning Research Journal. And there is this deals only with the discrete time problem, and that's what I'm going to focus on here. But a much expanded version of that can be found as an archive. And if you haven't noted this or are interested in this paper and didn't get a chance to write it down, I can send it to you if you can send me an email. So the linear dynamical systems is in this form. Z is the output, and W is the input disturbance. U is the control, and you have both continuous time and discrete time, and this is a representation of that system. You have the transfer function from Z to from W to Z in the continuous time given in this way, and in the discrete time given in this way. So we're looking at the H infinity norm of the system, which is the maximum singular value of the H. K in the discrete time, and I mean in the continuous time, and is the maximum eigenvalue, square root of the maximum eigenvalue of this. in the over all possible frequencies in the discrete time. So I'll be, as I indicated, I'll focus on the discrete time setting. So what we are interested in is minimizing J of k such that the objective function, such that the stability condition is satisfied and the H infinity bound is satisfied. Now, there is an explicit expression that one can obtain for J of k, but this is only an upper bound. You know, it upper bounds the H2 norm, so that's what we are going to work with. But this is also exact for the sensitive control problem, as I'm going to show shortly. So the important thing is that the J is given in terms of the solution of a Riccati equation for each k. Given k, you solve this Riccati equation. Note that we are dealing with an infinite horizon problem, and so therefore, any policy gradient method that we would be interested in is would of course be applied to this objective function, or this one. They are equivalent. The two are equivalent. And so this is what I would call the classical formulation optimal control with robustness considerations, minimizing this. Now, with sensitive control as a history going back to David Jacobson in 1973, a transactions on automatic control paper, and this is the economists have used it a lot since then, and still it's an active research area because it has embedded in it a certain element of robustness, as we're going to show. So instead of minimizing, in the case of linear exponential quadratic Gaussian problem, instead of minimizing a quadratic function, you minimize the exponentiated version of a quadratic cost function. And of course, you have stochastic, this is a stochastic system now. You have an input, which is a Gaussian random variable, Gaussian sequence with covariance W and mean 0, and initial state is also Gaussian with 0 mean and variance x0. Okay, so what this does is essentially it emphasizes unfavorable paths. This is a stochastic system. A stochastic system is many sample paths and many possible realizations, and it essentially puts more weight when you exponentiate things. You put more weight on the more unfavorable paths, those that are reflected in the cost function, than the more favorable ones. So therefore, there's a robustness sort of an element embedded in it. And so this is the infinite horizon version, because we take the limit lim sup as t goes to infinity. And there exists, so you cannot allow data to be very large, because then the problem becomes too, the individual who is, note that there's a single decision maker, this is the controller, the individual is too pessimistic, and there isn't much you can do. Regardless of what you pick, the value is going to be infinite. So there's a natural bound on beta. If beta, this is like in H infinity optimal control, the bound on gamma, which is in the, as I'll show on the next slide. So, so there exists a beta star, which depends on the parameters of the problem, such that if beta is larger than beta star, then there's a minimum. Otherwise, if beta is larger than beta star, then this is infinite. So that's what we are interested in. And in this case, the minimum of J exists, and one can actually show that the solution in this case is unique when this condition is satisfied, and you have a linear solution. The control is linear in the state. So you have linear state feedback. So again, if you want to do any parameterization for this problem, then a linear parameterization does not lead to any loss of performance or a loss of generality. So you are not losing anything. And you can actually, the equivalence is that if I take Q to be C transpose C and W to be D transpose, note that this was the disturbance weighting, disturbance gain in the mixed design problem. And then U is minus KXT, and the feasible set for this problem coincides with the feasible set that I had obtained earlier. So instead of this being less than gamma, I have this being less than 1 over square root of beta. So therefore, the square root of beta corresponds to 1 over gamma. Okay, so if I do any policy optimization for this, I would also be solving the mixed design problem. So again, it suffices to search over LTI controllers, and the modified Bellman equation. This leads to a generalized algebraic Riccati equation in the solution of this problem, which is given in this form, and this is for any fixed k. So you fix k, and as I indicated, there is a unique k that satisfies, that minimizes this. So the minimum exists and it's unique. And again, this lemma shows that the j of k, so once you parameterize the control in terms of k, and you have introduced a Riccati equation, which generalized Riccati equation in this way, then in terms of p sub k, you have this expression, which is the value of jk for a given k, assuming that this condition on beta is satisfied. Okay, so these two conditions, actually, you need stabilizability. There exists a solution to this, such that it is stabilizing. That is, this is the stability condition, and it satisfies an additional condition on beta. And so this J is exactly the one that we had for the mixed design problem, and which was an upper bound for the H2 norm. So there are, this formulation also covers maximum entropy, H infinity control, and which is, has been shown by Glover and Doyle in 88 and 89, by Mustafa in 89, as well as it is connected to linear quadratic zero-sum dynamic games. And I'll say more about this later. Actually not. Now for this LQ zero-sum dynamic games, you bring in, as I indicated at the very beginning, you bring in another player, another input V sub t, active player, and you solve, instead of an exponentiated cost minimization problem, you solve a risk neutral one, but with a soft constraint on V and with a gamma squared here. And so if you solve for the saddle point of this, the corresponding control is exactly the one that you have in the exponential cost problem. And so therefore this is essentially the same. And but of course here the optimal control pulses are identical, and the beta in that case is the same as 1 over gamma squared. And but also now here you have an additional input which didn't exist in the other case, which is V is equal to minus LXT. So another problem of interest is, can one obtain a policy optimization for such games as well? Because essentially the control that we should end up with, the K, will be the same as in the both in the mixed design as well as in the linear exponential quadratic Gaussian control problem. But the thing is, there is an additional element L which we don't know, and the question, there are counterexamples one can show that if you iterate on K and L either in parallel or in some other fashion sequentially, this does not converge. Okay, so one has to be more careful in addressing how to handle L in this case. And that's connected to adversarial reinforcement learning. And again, as gamma goes to infinity, note that what happens in this case is you are putting infinite cost on the adversary's input. And so therefore, the adversary essentially picks 0, and you have the linear quadratic regulator problem. So again, as gamma goes to infinity, this is, you end up with a single constraint instead of multiple constraints. So, so this is what we want to solve, therefore, which has connections to all these problems. And we want to design policy, we have policy optimization for these. Now, let me, maybe I'll include this also. The difference between what is the challenge, main challenge here, the difference between the LQR and this mixed H2H infinity, as well as the LEQG, which is the same. Now, in the LQR, you have the spectral radius condition only, has to be less than 1. But the important property is that you have, it is non-convex, but it is coercive. That is, as K reaches the boundary, then the J becomes very large. So therefore, if you move in the direction of decline of J in your algorithm, if you pick an algorithm which at every iteration moves in the direction of in the direction opposite to that of the gradient, then you stay in the feasibility region. But that's not the case with H2H infinity because of the H infinity constraint. You can easily reach the boundary without, if you are just looking at how the values of J changes, the J does not go to infinity, but you may be outside the feasibility set. So that's the main sort of one of the difficulties that one has. So the JK descent cannot ensure feasibility. Then the question is this. So this is the one of the challenges. How can we enforce that K remains in script K? And that is, for example, you have this is H infinity norm is a sort of it provides a safety consideration. So you don't want to go outside the safety region during the learning process. And the question is, how can one develop algorithms such that this happens? So we have looked at 3 possible algorithms. The policy gradient, note that this is the gradient of JK, and which can be written in this form. Explicitly, you can compute this. You have the natural policy gradient where you multiply this by this lambda inverse of lambda k, where lambda is given by this solution of the Lyapunov equation. There is the natural policy gradient, as I said, where you get rid of this additional term here. And there is also the Gaussian Gauss-Newton method, which is you multiply this from the left by this term. So what this natural policy gradient, this policy gradient over Riemannian manifold, as it has been shown 2 years ago. And Gauss-Newton, when I set, these are the step sizes. If I set eta equals to 1/2, it reduces the policy iteration for game problems, for linear quadratic games. So, so what we need is regularization. That is, we want Kn to be confined to K during the iterations. So that's sort of the robust stability problem. One way of ensuring this, if you want to stay in a constraint set, is to do projection. But this will not work here because K is non-convex. So what we have shown in that long report, that the two of these algorithms, the natural policy gradient and the Gauss-Newton, they implicitly regularize the iterates. And they therefore preserve robust stability automatically, provided that you take the step sizes in a certain way. And these are the bounds on the step sizes. The Gauss-Newton, eta has to be less than or equal to 1/2. And for the natural policy gradient, we have to take eta to be less than 1/2 times the norm of this. Then we can show that if K, with these step sizes, if I start with a particular K, then at the next iteration, I stay in script K, regardless of. So therefore, this shows that for all, at every step of the algorithm, you remaining in K. So therefore, what this shows is that the general descent directions of JK do not work, but certain directions do. So the proof, maybe I'll skip this. We use bounded real lemma for to prove this. It's a lengthy proof, this result. And so the bounded real lemma tells us that being in K is equivalent to generalized algebraic Riccati equation, admitting a unique stabilizing solution which satisfy these two constraints, or what is known as a Riccati inequality. There exists a P such that this condition is satisfied. And this is, again, if you interpret it in the context of games, what this says is that the cost function is strictly concave with respect to the control of the adversary. And so P tilde is given in this. Okay, so essentially the proof technique is based on LMIs, and we use this, we show that the bounded real lemma holds if and only if the Riccati equation condition holds if and only if the strict Riccati inequality holds. And we construct a solution to a non-strict Riccati inequality and do some perturbation on the Riccati equation that leads to a strict Riccati equation and so on. So, so the main theorem, or one of the theorems, is that if we have start in K, and where the norm is finite, and if we have this condition, controllability of this pair, and at the stationary point K, then under these step size choices, both the Gauss-Newton and the natural policy gradient updates converge to the global optimum at the rate of 1/n. And the controllability assumption follows from an earlier result, but this is not does not bring in any restriction for the exponential cost problem, because it's automatically satisfied in that case. So therefore, for the LEQG problem, essentially, whenever you start in K using these two algorithms, you converge at 1/n rate. These two algorithms, Gauss-Newton and natural policy gradient, with the given step sizes. Now, in LQR, there's a very nice paper from ICML in 2018 by the University of Washington group, where they show global gradient domination, but this does not hold in our case, and for that reason, it's only 1/n rate globally. Now, locally, if you start closer to the, fairly close to the solution point, then one can show that you have superlinear rates around the optimum. So this is this very quickly. This shows the. I'm not sure whether you are able to read these, but the red one is the gradient algorithm, and the blue one is the natural gradient, and the green one is the Gauss-Newton, and this one is the Gauss-Newton, the pink, purple one, Gauss-Newton with step size 1/2. Okay, so here the step size is Gauss-Newton. The step size is 0.1, less than 1/2. So these step sizes satisfy the given constraints, and here you can see the difference between the JK and JK star. The purple one, that's the Gauss-Newton with step size 1/2, converges much faster than the green one, which is where it's 0.5, and so on. And this is what shows the H infinity norm of the resulting H infinity norm. Now, if you initialize near the boundary delta K, that is, if you are closest to either the robustness margin or the stability margin, then it takes much longer. It still converges, but it takes much longer in terms of the number of iterations to converge. Okay. So there is, as I indicated, H infinity. I think will be good. How much more time do I have, Shreyas?
I think probably since we started a little bit late, if you maybe within 5 to 10 minutes, if you could.
Sure. I'll wrap up in
thank you.
5 to 10
Thank you.
So let me just mention one maybe last topic here. I indicated that that there is a strong connection between LEQG and zero-sum games, as well as H infinity control and zero-sum games. So for the zero-sum games, you have an additional input, which is the control by an adversary, and again, now the parameterization here, for parameterization, you need both for the control as well as for the adversary's input. So therefore, there are two matrices, K and L, and one can actually show that under this objective function, or the objective function that I had earlier, which is quadratic, there is a unique saddle point equilibrium here, or the Nash equilibrium, if you may call it. And so therefore, this parameterization is an optimal parameterization. You are not losing anything. So the question here is, so you substitute for u equals to minus kx, v equals to minus lx, and you obtain an objective function which depends on k and l. So you are doing minimizing with respect to k and maximizing with respect to l. And since we know that a saddle point equilibrium exists, this is the same as maximizing with respect to L and then minimizing with respect to K. And this actually is a baseline. There's a lot of interest currently on what's called robust adversarial RL. And this is to the reason why there is so much interest in this is because people have observed that there is a gap from simulation to real. You do simulations and then you apply it to real systems, and then things do not work as you would have expected from the simulations. So therefore, the adversarial sort of RL has been introduced within the Markov decision process formulations. So this is, in this framework, this captures that. And so the thing, what one would do is, there are many different ways of if you have two parameters or two parameterizations and you are minimizing with respect to one, maximizing with respect to the other, you can do a policy optimization and take turns between K and L, or do it in parallel. And it turns out that this does not work. And so you have to do things. So we introduced what's called if we fix K and then do maximization with respect to L, which is an inner loop, and then come back and minimize with respect to K, which is the outer loop. Now, for each fixed L, we know that we already know what the earlier results. So this is just a policy gradient with respect to K. So we already know the conditions under which that converges. The question is, how do you handle this inner loop? And so what we have shown is that there has to be some time scale separation. In other words, if you are able for each K to find the best L, maximizing L exactly, and you can guarantee that this maximizing L will not drive the system to infinity, provided that you restrict K to a certain set, then you can apply what I discussed up to this point for a policy optimization for K, and then that leads to the convergence results that we were looking for. So then the question is, well, if we cannot do exact optimization, maximization with respect to L for each K, what if I do approximate solution? In other words, I use policy gradient, but I stop at a certain epsilon optimality. Can we still do it? And so we have results which show that yes, you can do it. So which suggests a sort of a 2-time scale optimization for this. And we have a paper. I mean, a paper which was in 2019 has shown that this, if you take alternate sort of optimization, that doesn't work. And so therefore, the more recently what we have done is, so here is what could go wrong. If you do alternating gradient or gradient descent asset, you think that things are converging, and then at some point, it goes out of bounds, outside the constraint set. Now, here, this is times 10 to the 4 in terms of the iterations. And you can see that each one of these are on different systems, that you can see that the stability is determined by this, of course, A minus BK minus CL. There is no other constraint here. There's no H infinity constraint, and you easily go out of bounds. So you have to avoid this, and so we have a paper which talks about this in the recent NIPS conference, again with Kai-Ching, Bin Hu, and myself. So then we talk about how one can pick the initialization and the update rules such that this can be avoided. So I'm going to go all the way to concluding remarks. So what I have discussed is sort of something toward a better theoretical understanding of policy-based methods in learning for robust control and risk-sensitive reinforcement learning. And I have advocated the use of H infinity norm constraints in assuring strong robustness for RL in continuous control tags. We have both mixed H2 H infinity and with sensitive optimal control, and more recently the zero-sum game results. The implicit regularization is very important in this case, which distinguishes these problems with robustness considerations from those where there isn't a robustness consideration or an element. And so we have to, implicit regularization essentially ensures that the robust stability is ensured during the learning process. And so for linear quadratic zero-sum dynamic games, we have this parallel versus inner-outer loop updates, which I didn't have that time to discuss this. And so we have more recent results on sample complexity, like derivative-free methods. How do you compute the gradient, for example, without taking the derivatives, and what would be the impact of this on the convergence? And there's mixed design for other types of dynamical systems. Now, one might be interested in sort of coming up with gains, control gains that minimizes the H infinity norm itself. And note that we had a bound on the H infinity norm. But if you want to, so that's a different problem, and it's non-smooth. Minimizing the H infinity norm is would provide it's not like continuously differentiable as the ones that we had. And so if this is of interest, some other sort of techniques will have to be introduced. And at the higher level, what I have really tried to convey as a message is that it's important in most safety critical applications to take into account the possibility of leaving the safety region during the learning process. And that could happen easily. And so you have to develop algorithms to make sure that that does not happen. And at least in this context, we have been able to obtain such algorithms. Okay, I'll stop here. Sorry for going over by about 9 minutes, but I think since we started a bit late, I think I took exactly 60 minutes. Thank you.
Thank you very much, Tamer. And it's a great seminar and talk. So we will go to briefly the Q&A. So for the audience, please type your questions in the chat window or unmute yourself to ask questions.
Tamer, this is Martin Corliss.
Oh, hi, Martin.
Nice to see you. I have a question. Do you think you could do better with dynamic controllers?
Sorry, you mean dynamic programming?
No, dynamic controllers. So you're looking at static
yes.
state feedback
Yes.
controllers.
This is actually one of the current research topics. Now, let's say that you have, I mean, the mixed design problem, or the let's say that you look at the LEQG, but you don't have perfect state information, but you have access to noisy state. Now, for that problem, it's known that the solution is again linear, but you have a Kalman filter type of filter equation which will estimate the state. And this is more like an H infinity filter. So the parameter gamma also enters into that, as well as into the controller. Now this, so therefore in that case, you are looking for two different, well, the same parameterization, but one for the control gain and one for the Kalman filter, or the dynamical, if you want to call it a dynamical system. You have another one for that. And so that is again a very non-convex problem, and it's much more complicated than the one that I have discussed here, because you cannot obtain the gradients the way we have done here. And one possibility is, as we have done in the linear quadratic zero-sum games, where if you do alternating sort of optimization, things do not converge, and you have to do some time scale separation. And so this is a problem that we are looking at, and it appears like some time scale separation there again will work. That is, the filter game you do on a faster time scale, and then the controller gain on a relatively slower time scale. But yes, this is would be an immediate, but well, immediate in the sense that this is what one would think of. And thanks for bringing this up. And but still, the theory, complete theory, is not there.
Okay, thanks.
Tamer, there is a question in the chat window. It's from Yao Ji, and his question is how to design and derive the robustness function TK of the system generally.
When the system is what?
I mean, more like how to design and derive the robustness function TK of the system in general.
Oh, well, if you have a linear quadratic problem, then that constraint becomes as I had on one of my slides, a solution to a generalized algebraic Riccati equation. So now, if you have a nonlinear systems, of course, then I mean, there isn't even a general H infinity optimal control theory for that. You can only do approximations. But for the class of systems that I have, the H infinity constraint on T is captured equivalently through existence of a solution, positive definite solution to a generalized algebraic Riccati equation.
Another question from Gosh, and he said, "Is this two-time scale dynamics can be seen at the Stackelberg game?"
Yes, because I mean, it's a special type of a Stackelberg game because this is in the case of the zero-sum game framework, and where you fix K, which is the controller game, and then maximize with respect to L. And then you come back, and let's say that you are able to do this maximization for every K in the feasible set. And there is actually an expression. We have an explicit expression for that in the paper. And then you come back and minimize with respect to K. So you can view the controller as the leader, and if you want to look at it as a Stackelberg game, and the adversary as the follower in that case. Okay, so the leader will take in your minimization with respect to K, you take into account the response of the adversary, which is L of K. And so therefore, yes, subject to that, to the constraint imposed by that response, you do your minimization with respect to K. And there, if you are able to solve for L of K explicitly, which we can, but if you want to do this in a model-free way, of course you don't have access to that expression. But let's say that the adversary knows the model exactly, and then if you do substitute L of K, the maximizing L for any K, and then you have an optimization problem with respect to K only, minimization problem, and then the theory that we had developed earlier applies. And what I tried, that part was very fast, but what I tried to say is that even if you are not able, if you are doing this maximization with respect to L in a policy optimization framework, and then even if you are not able to have a perfect maximizing solution, still you are okay. And but there is an epsilon delta argument there. But the bottom line is that yes, you can view it as a stackable game, where the controller is the leader and the adversary maximizing the objective function is the follower.
Thanks. Any other questions? Feel free to. Okay, I got another one from Wan Xinjing. He said the policy gradient in RL is favorably model free. Are all the methods presented here requiring the knowledge of dynamics model, or any progress on the model free case?
Well, we have some sample complexity results where we do not, which is based on just sampling the return based on choices of K, and it is you have to know the order of the system at this point, and if you don't know the order of the system, then things get a little bit more complicated. Yes.
Thank you. So, any other questions? If not, let's thank the speaker again. So, Tamer, thank you very much for your great talk.
Sure.
And I believe many students and faculty here had already benefited your very earliest work on multi-agent reinforcement learning. So in the next, we will have a meeting between you and also our econ faculties and young researchers. So to host that section, I would like to introduce our new faculty, Philippe Pierre. You have known very well. And he graduated from UIUC and joined the Purdue ECE as an assistant professor. So Philippe, it's all yours. Now you are in charge of the rest of the event.
Thank you so much. And Tamer, thank you for the great talk. Can everyone hear me?
Yes, I do. And let me do, I'll stop the sharing because would my slides be needed? Probably?
No, that's fine. Yeah, that sounds great.
And maybe we stop the recording as well.
Yes.